All right, so we're doing algebraic approach to limits. This is part 2 of the notes. So had to cut it short yesterday. So let's see. This one says find the limit as x approaches 2 of 2x plus 5 over x minus 2. And so our first order of business is always just to plug it in. So we'll get 4 plus 5 over 0. Wait a minute. I got 9 over 0. Guys, that's not 0 over 0. This is not an indeterminate limit. We are able to determine this limit. So you might remember before when we would do these problems, we'd get 0 over 0. We'd find something that cancels, and then we were able to get a number. When something doesn't cancel, instead of making a whole, it's going to make some kind of asymptote. And we're not sure if it's going to be like, if it's going to be this sort of asymptote where it goes like up to infinity and comes back, or if it's going to be like the kind where it's going down and then coming back, or some situation where they're both going up or both going down. We don't know. And so what we do to figure that out is we test ever so slightly to the right and ever so slightly to the left of our x value. So what I'll do is I'll test, like, you can do this test mentally, you can do it out by hand, but the big idea is we know it's going to either positive infinity or negative infinity. And so the real deal here is the number ever so slightly to the left of 2. We know that's our asymptote, but ever so slightly to the left, what's our numerator? Is our numerator going to be positive or negative? Well, ever so slightly to the left, like that'd be like 1.9 or something like that. 1 point blah, 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 times 2 plus 5. That's still a positive number. And then what about something like the denominator? So at 2, it's 0, but ever so slightly to the left at like 1.9 or 1.8 or 1.999, it's a little bit under. It's going to be a little bit negative, and so because of that, it's that. And then remember, it's just the top divided by the bottom. So the top divided by the bottom, is that positive or negative then? And so since positive divided by negative is a negative, I know that this is going to negative infinity. I can analyze that and think about that. And so I didn't even have to do any of the work. I just had to kind of think about it. And so similarly, if I go slightly to the right and like 2.001 or something like that, well, the numerator is still going to be positive. The denominator's going to be, this time the 2.001, we're going to subtract the 2 and we're going to be left with a little bit of positive. And so that tells us that side's going to positive infinity. So if it asked me, hey, what's the limit as x goes to 2 just from the left-hand side, we'd be able to say it's negative infinity. Or if it was just from the right-hand side, we'd be able to say positive infinity. But since we have these two disagreeing left and right hands, we have like this scenario here. Because of that, we can say our limit is D and E. The left and right hand don't agree. Limits don't agree. To me, this is legible. So you might know why I was talking about how some people's stuff was called illegible by my student aide, and I'm like, I don't know what you're talking about. To me, it's super legible. All right, let's look at our next one. So on this one, again, we get 4 over 0, which is not indeterminate. It's something that we have to actually figure out. And so I like using these kinds of charts. I use them for a lot of different things. So you don't have to use them. There's plenty of other ways to kind of reason this out, but I think that these are really helpful and really a good way to organize our thoughts. So wait a minute, 4 is always positive, and so there's my asymptote. So 4 is always positive. But x squared, if I go over to so if I plug in a slightly negative number and square it, I still get a positive number. And over here, slightly negative or slightly positive number, square it, we still get positive. So this time when we divide the top by the bottom, we're getting a positive infinity over here and a positive infinity over here. So even though they're both going to infinity, they're going to the same infinity. So that's like this scenario right here. And so we're able to say that our limit is actually equal to infinity. So, sorry for the slurpy noises. I'm drinking tea to hopefully help me not feel like junk anymore. All right, let's see what's next. So on our next one, it says the limit as x approaches -3. All right, so I'm going to plug this in. This one, I wind up getting, let's see, 9 minus 6 minus 3. Okay, I do get 0 on the bottom. I mean, whoop, that's called the top. I do get 0 in the numerator. And then in the denominator, I think I'm getting 0 as well. Yeah, I'm getting 0 over 0. That means I can do simplifying. So I can factor the numerator. And I talked about factoring more in the last video. Cool. Do some factoring, do some canceling. Uh-oh. Now when I plug in, remember I haven't actually plugged in yet, so I should write the limit notation. Now when I'm plugging in, I wind up getting -4 over 0. So now I'm over 0, but it's not indeterminate anymore. And so because of that, I am now able to do this analysis. So I'm going to check out -3. I didn't used to have a consistent way to write these tables, but it really helps my students when they have a nice consistent way to think about these tables. So let's see. If I think a little bit to the left of -3, this first one is negative. This one also is going to be negative. Hey, what's a negative divided by a negative? And then if I think a little bit to the right, I might have said right over here by accident, thinking back, but if I think maybe 2.99, -2.99 over here, well, this time that's still negative. There's my asymptote. That's still negative. This one is positive this time, and so we get -infinity. This is honestly more common, having them disagree with each other and getting D and E. Much more common than this. And the reason is, this happened because of the squared, and things like this happen because signs change at different points. And so when we actually have sign changes, that's when we run into them. So now when we look at example 3D, okay, I do get a 0 in the numerator. I'm going to assume I get 0 in the denominator. No. You know what happens when we assume? A lot of times we're right, but then sometimes we make mistakes. So let's see, 8 minus, I think that's how that phrase goes. Excuse me. I'm going to say there was like a dog that just walked by and did that. It wasn't me. It's 24, that's 24. So we do in fact get 0 over 0. Okay, I'm a little skeptical about factoring this, in all honesty. So like I try to factor, and I'm really struggling. Because if I pull an x squared out of the first one, then I'll get x minus 6, but I don't get an x minus 6, and the biggest thing I can pull out here is a 4. So those don't match. This doesn't factor in that fashion. And I've thought about rearranging it to see if I can do it, but I'm not seeing anything that's going to make this work. And so because of that, I am going to factor the numerator, though. I'm able to pull a 2 out and say this is, you know what? Hold on, don't be fancy. I'm going to pull a 2 out and say that this is 2 minus x. And if I were to change that to a -2, let's just talk about this off to the side really quick. So this is a very clever trick that I did not think of, so I'm allowed to call it clever. Instead of pulling a 2 out and getting 2 minus x, what if instead we pulled a -2 out? So if I were to pull a -2 out, then I could write this as -2 plus x, or better put, negative 2 out front of x minus 2. And now it's in that standard order that we're used to thinking about. So generally, what I do, when I see that the x is second, I see the 4 minus that, when I'm trying to factor this, I will just say, okay, I'm going to factor a negative out, and I can factor a 2 out. And so I switch their order. So my inclination is that this is the way we're going to have to handle this problem. So, and the only way I know how to factor this is using synthetic division, which is everyone's favorite. So I believe that instead of doing that, though, our book is suggesting to us that there is a better way, and there is actually a better way that I can't teach it to you yet because we don't know derivatives yet. But once we learn derivatives, we're going to learn a special trick to handle these. And there's a long mess of a way to do this. For now, we're going to say this is indeterminate. Just for now. In the future, we're actually going to find out what this limit is. We're going to find out if it's a number or if it doesn't exist. But for now, we're going to say it's indeterminate. For now. All right. So now we're going to have to use a little bit of common sense. And this is a special limit right here. Limit as x goes to 0, sine of x over x. This is one I'd actually recommend you go to your calculator and look at. Make sure you're in radian mode. If you have physics, you're going to have to make sure you go back and forth. Physics, they usually use degrees. But hold on a second. All right, so recommend going and checking this out in the calculator, and the answer is actually 1. It's undefined at 0, like f of x is undefined at 0, but the limit is 1. Now this one, we get 0 over 0. At this point, we don't know how to do it yet. So for now, we're just going to say it's indeterminate. This is never going to be an acceptable answer on the AP test. They're never going to give you one that we can't do. And we're going to learn how to handle this one later. Similar with this one, we get 0 over 0, and who knows how to handle it. So, womp womp. So these ones are, right now, these ones are tough, or impossible for us. We're going to get to a point when they're super possible, and honestly, kind of easy. But that's not yet. All right. Now we get into piecewise functions. We call them piecewise because it's a bunch of pieces put together. So I know, really complicated definition there, but so we get to these ones. This one says, hey, what's the limit as x approaches 1? And so what we're going to want to do is we're going to want to look at the left-hand limit and the right-hand limit, because let's back up. Okay, the thing that's going on here in a piecewise function, so the graph of x squared minus 4, that looks like this normally, right? Well, this one says f of x is this picture as long as x is less than or equal to 1. And so that means at the x value 1, we have a dot because it's got a line underneath, and it's anything to the left of it. That means all this over here is not there. Instead, what happens is this negative 3x plus 1 shows up. So the line that looks like negative 3x plus 1, that one starts when x is 1, but notice how there's no line underneath, so it's an open circle, and it goes forever. So we are basically trying to figure out, so this was our left-hand limit, and this was our right-hand limit. I should have drawn them on either side of each other so we can think about it a little bit easier, but let's look at what their y values are approaching. So I'm going to plug in 1 to this one, And I get 1 minus 4 is negative 3. Okay, so this one, this is the limit as x approaches 1 from the left-hand side. We get negative 3. Now from the right-hand side, we're going to use 3x plus 1. Oh, I should write f of x there. But f of x. And this one I get negative 2. So the left and right hand are not going to they're not going to the same number. So since the left and right hand are not going to the same number, this limit does not exist. Now let's go to our next one. Whoa, our next one has 3. So if we're paying attention, we can see that this one is 2 and less than 2. This one is just when we're at 2. So this would be the filled in dot when x is 2. And then this one is going to be everything greater than 2. And so what we're going to want to do is we're going to see if the two that overlap at 2, we're going to want to see if they equal each other. Because, it could be like this sort of scenario, right? It could be one of those things. But in that situation, the limit is fine. So I'm going to try plugging 2 into both of these. So I plug it into the first one, I'll get 4 plus 6 minus 4, and I get 6. Then this one, I get 2 cubed is 8 minus 2, I get 6. All right, I'm back. That was Tovar's fault. So we got 6 and we got 6 when we tried the left, when we tried the right. Remember that at the actual point, we don't really care. So even though they're not 4, then they're both 6. Since they match each other, the left and right hands match each other, then our limit is 6. So let's try this one. When I try negative 3, whoa, this one's crazy. When I try negative 3 here, that's an asymptote. But it says it's less than it. So I want to figure out, is it going up to positive infinity or is it going down to negative infinity? So I'm going to check just a little bit to the left of negative 3, like negative 3.001 or something like that. And that's going to give me a negative on the top and a negative on the bottom. So this one's going to positive infinity. Now this one, I'll check just a little bit to the right of that, which is in the negative 2s, the high negative 2s, like negative 2.9. The numerator will be positive, the denominator will be positive. That's also going to positive infinity. So I can say that even though these are different functions, both asymptotic at negative 3, they're both going to positive infinity. I'm a little worried that oh, I didn't need to write the plus. A little worried that explanation is not super helpful, a little bit too fast, but feel free to ask me about that one. I'd rather work with somebody individually on that one. Okay. We need, let's see, I like to ignore his blocks of text and just kind of talk about things because he has helpful ways of doing it and I do things slightly differently sometimes. But either way, we're kind of arriving in the same place. So this says find the limit as x approaches infinity of this over this. Ah, okay. So if you understand horizontal asymptotes, you understand limits going to infinity. So the way that I like to talk about this is as x gets bigger and bigger and bigger and bigger and bigger and bigger and bigger, 4 times a bajillion, and then you subtract 3, you basically have 4 bajillion. And then 8 times a bajillion, and then you add 1, you basically have 8 bajillion. So you really got 4 bajillion over 8 bajillion. And the bigger the bajillion gets, the more it looks like just that 4 over 8. And so 4 over 8, or 1/2, is actually the limit there. And it's the exact same idea as a horizontal asymptote. So here on this one, and so I don't like to use the 3 cases, and he's going to use the 3 cases to talk about it. I like to use the singular case of find the greatest exponent. Because here, this is 6 bajillion on top, but on the bottom, it's bajillion times bajillion. So in both cases, those are like not there. But bajillion squared, or a bajillion squared, bajillion's not a number, is so much bigger than just a regular bajillion. And so because of that, this might as well not be there. And it's really just like saying, wait, there's nothing on the top anymore. It's basically saying there's nothing up here, and there's a huge number down here. And so 0 divided by a huge number, or like any number divided by infinity, like we're saying that that's this compared to this is like a baby, and that is like gigantic. So this is actually going to be 0. And then our last one here, hashtag slant asymptote, if you remember your cases, but you don't need to know the cases if you just think, oh, I see x to the 4th. So on the top, I've got 2 bajillion, or 2 times infinity. On the bottom, x cubed. I don't have an x to the 4th. And so I could say I don't have any x to the 4ths. So infinity divided by 0. Normally we can't divide by 0, but we're just thinking about this in terms of limits. The number on top gets bigger, 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 bigger. Compared to the bottom number is just a baby. So because of that, this one's actually going off to infinity. So if this line of reasoning doesn't work for you, if it's not making sense, there certainly is a case by case. These are the 3 possibilities. Use this, it will always work. I like to do this way though, so I just find, okay, I see x cubed is the highest power. I've got 1 x cubed on the bottom. I've got no x cubed on the top. 0 divided by 1 is 0. This one, and this is only when the limits are going to infinity though. If they're going anywhere else, we have to think more about it. So this one, x is going to positive infinity. So I see 4x cubed on the top, and I see an x cubed on the bottom too. I see 5x cubed. And so because of that, this is going to 4/5. And this is just an application of the horizontal asymptote rule. So similarly, number 7c, I see 2x to the 4th on top. I see no x to the 4th on the bottom. 2 divided by 0, we're going to call that infinity. So note, in all of these situations, f of x, or the y value never gets to 0. The y value never gets to 4/5 as we go out this way. It never gets to these numbers. It just approaches it as we go out to infinity. And that's something that's really, really weird. You keep going to the right, and it gets closer and closer and closer, but it never hits it. This one says the limit as x goes to negative infinity. There is a secret trick for these ones, and that is that 1 is going to be pointless, but that we could think about this as an x to the 1/2 power. I want to remind you, square roots are the same idea as the 1/2 power. So where's our biggest power here? And the other thing that we should talk about is, since we're going off to negative infinity, there's something a little bit different to talk about. When we're going off to negative infinity, we're going to want to think about, okay, negatives and positives and that sort of thing. Because in the numerator, we're going to subtract 1 minus infinity, and then we're going to take the square root. 1 minus negative infinity, right? But then we're going to take the square root. So that's going to be the square root of a positive number. We're going to wind up getting a positive number on the top, and then negative infinity on the bottom. And so because of that, a positive divided by a negative, this one's actually, it's a number over infinity. It doesn't matter if it's positive or negative infinity. Number over infinity is 0. So I just kind of spent way too much time on that. A number over infinity is just 0. And our next one, you might say the highest power is x squared, but be careful. The highest power is the square root of x squared, and then the square root of whatever that is. So, but the square root of x squared, think about that. That's just x. So it's x to the 1 that's on top and a 2x on the bottom. And so our answer is actually going to be 1/2. And then here's the weird one. It's fair to say the bottom of this one goes to because this one's going to negative infinity, where e was just going to positive. So this one says, hey, the bottom's going to -2 infinity. The top, check it out, it's because we're taking a negative, we're squaring it, the negative goes away, and it's just a positive infinity, and then we take the square root. Or like a positive infinity squared, and then we take the square root. And so because of that, the top's just going to be regular 1 infinity. And so our answer for this one's going to be -1/2. All right. And now we are going to kind of extend this idea, and we're going to extend it, and we're going to talk about size of infinity. Think about x versus e to the x. Okay, we're going out to infinity. So x is this linear thing. It's going up, it's going up, it's going up. E to the x is this exponential, goes swoop. And we want to think as we go out more and more out to infinity, you know, we're going to be at 1 billion, and then 1,000,000,001, and then 1,000,000,002. This is going to be e to the billion, e to the 1,000,000,001, e to the 1,000,000,002. This one, for every one that we go over, we go one up. For this one, for every one that we go over, we multiply the y value by e, which is over 2. It's like 2.7. So this one we're multiplying by almost 3 every single time. This one we're only moving up 1 unit every single time. If you can kind of think about how that would affect it, this e crushes the x, and the x may as well not be there, and so it winds up being like 0 over infinity, and it's just a 0. This next one, e to the x and e to the x, they fight each other, and they're like the same. And that +4 and that -4, when we're out with 80 bajillion zeros, it's like, who even cares? It's just e to the x over e to the x. It's just 1. And then this one's kind of funny. Sine does this, right? Whee! The biggest or smallest sine is ever going to be is -1. But it's whee over infinity, right? Because we're going out to infinity. So like, -1 over infinity, or 0 over infinity, or 1 over infinity, like those are the smallest and biggest sines ever going to be. Those are all the same answer of 0, a number over infinity. So, and that's really it. I'll leave my answers up here. Feel free to pause the video if you want to check my answers to the first 14 homework questions, because that's what I did for class today. I'll upload what I get for the rest of them eventually. Nothing too outlandish. So remember that whenever we have one that doesn't fit into any of the molds that we've seen so far, for now we're going to say it's indeterminate, but in the near future we're going to learn a special trick to handle it. And that's really the end of section 5. So this book has 24 sections. We're already a fifth of the way through this book, but the entire school year, we're really trying by the beginning of April to get through all the way to section 41. So is 41 the very last one? No, 42. So we're gonna get all the way into 42 different sections. So we're off to a great start. Some of these are gonna take a lot longer than others. And a couple of you have messaged me through Schoology. That's awesome. Feel free to get in touch with me anytime. It's no problem to get back to you. Even if I'm not your teacher this year, feel free to email me or swing by. Love to help you out. Have a good one. Bye.